Good morning, learners. This is Mutsiele Tena. I will be presenting to you physical science, and we are going to spend the next few hours, 2 hours to be exact, dealing with vertical projectile motion. As you know, we have our famous equations for the motion of an object that is experiencing a uniform acceleration. And these equations, I have indicated them here as the first equation, which is F final is equal to Vi plus A delta T. And then we also have V final squared is equal to Vi plus 2A delta Y. Delta Y is equal to Vit plus half AT squared. And the last one says delta Y is equal to Vi plus Vif, which is final, divided by 2 multiplied by delta T. As you know, learners, these equations are found in your information sheet. And what I would advise you to do is to know these equations generally by heart, because it helps save time when you work with these equations to identify the quantities that you are given. Once you have identified the quantities of that you are given, you are able then to identify the appropriate equation that you can use to solve a particular question. My advice would be, if you are using equation 3, it would be most important for you to note that this equation can be easily used when your initial velocity is 0, especially if you are required to determine the change in time or the time. The reason here is that if your initial velocity is not 0, then this equation normally will lead to a quadratic equation, which might give us a problem. So avoid as much as you can the use of this equation when the initial velocity is given and you are supposed to find the time. You can alternatively use equation 1 and 2. And if you do that, you will find that you can use equation 2 first to find, say, the final velocity of an object. And once you have found that, you can substitute, or you can use the values that you found from equation 2 into equation 1, where you can be able to find the time without having to go through a quadratic equation. So you can just check when you use these equations that if I am required to calculate time, then I check whether I am given the initial velocity. If I am given the initial velocity, then that equation will probably become a quadratic equation. To avoid that, you can use the 2 equations, which will give you an alternative route to getting the time without having to solve the quadratic equation. Having said that, I am quite sure that learners, you are able to do this calculations in particular where you are using the equations. But what we have realized when we mark your scripts is that there is a little bit of a challenge in terms of the graphs of motion. So that is where I will start immediately, so that we can be able to solve problems hereafter. I will start with an activity, a simple activity, where I'm going to give you this particular problem is just an activity that we are going to do. In this particular activity, we are saying an object is projected vertically upwards with an initial velocity of 20 meters per second. Now what we need to do is to draw a position time graph, then a velocity time graph for the motion of the object over an interval of 5 seconds. For this activity, we will try to assume that our acceleration due to gravity is 10 meters per second squared. Of course, you know that in reality, our acceleration due to gravity is 9.8 meters per second squared. Maybe we will also extend this to draw an acceleration time graph for the object so that we can be able to see the relationship between the position time graph, the velocity time graph, and the acceleration time graph for an object which moves in a straight line, like a projectile, in this case vertical projectile, experiencing uniform acceleration. Now let's see how we can do that. Now to answer this, let's start first by in order for us to draw a position time graph, then we need to determine the position of an object. Let's say this is our time in seconds, and that will be the position in meters. We will take the time, that is the time when we start to project the object. We'll take the first second, third, fourth, and the fifth one. We know that according to the question, the initial velocity of the object, Vi, is equal to 20 meters per second, and therefore we want the distance that the graph will, the object will have traveled in this times. So for each of these times, we'll be able to find the position of the object with time, with respect to its point of projection. So the equation we are going to use will be delta y is equal to Vi delta t plus half a t squared, or delta t squared. Now we will, for this particular situation, take our direction as positive. Let's say up as positive. So we take the direction up as positive. Now here we are saying we want to find the position of the object y after 0 seconds. So what we will do is just to complete this table, so we will substitute the values that we have of time in the equation here. So you will see that when our time is equal to 0, then we are actually going to have our initial velocity, which is 20. But since we are saying up is positive, the object is projected upwards. And as it is projected upwards, the velocity initially is in the direction upwards. And that means, therefore, that it will be positive. We are multiplying by t, which is equal to 0, plus half of our acceleration. In this case, we have said it is going to be 10, But let us remember that when an object goes up, the acceleration due to gravity is always downwards. So since our direction up is positive, the acceleration is working in the direction opposite to that, which is going to be -10. Now we are multiplying this with a 0, so that will give us, here it will be 0, and there it will be 0 because we are multiplying by 0. So the change in position will become 0 meters. So our first coordinate there will be 0, 0. We can do this to say if delta y is equal to vi delta t plus half a delta t squared. Now what happens when t is equal to 1? Then we substitute there. Our initial velocity is 20. Our time will be 1 second plus half of -10, which is our acceleration due to gravity, times 1 squared. That will give us 20. This will be -10. Then the final position will be 10 meters. So we get our 10 there. Oh, sorry, this will be half of that, which is 5. So this is going to be 20 minus 5, which is 15 meters. So this is going to be 15 meters. We go on with the second one. When delta y is equal to VIT plus half of -10 times, in this case, delta y is equal to VI delta t plus, cannot do this, half of a got. Now what we can do is, apparently I have a technical problem. We will see that delta y is equal to VI delta t plus half of a delta t squared. This will give us, for v is equal to 20 times 10 no, the time is 2 plus half of acceleration, which is -10 times 2 squared. This will give us 40 minus 5 multiplied by 4 squared. This will give us 40 minus 20, which gives us 20. So here we have 20. And in the third one, if we do the substitution in the same way, we are going to have 15, we are going to have 0, we are going to have minus 25. We can go on to draw the graph for that object. I've already done this. You will notice that the first coordinate when t is equal to 0, when t is equal to 0, the position will be equal to 0. When t is equal to 1, the position will be 15 meters per second. Sorry, 15 meters. And when t is equal to 2, you have 20 meters. And when t is equal to 3, you have 15. And when t is equal to 4, you have 0. Lastly, when t is equal to 5, then you have minus 25. What can we say about this position time graph? What the position time graph tells us is the position of the object relative to the point where it is thrown. So we want to see what happens in time to the position of the object. The position starts at that, the object starts at that position where it is projected vertically upwards. And after 1 second, it has gone, it is at that position. After 2 seconds, it is at its highest point. At the highest point, this object changes direction and moves downwards so that it comes back to its original point of throw at time is equal to 4 seconds in this particular case. If we were to look at this object starts here, it goes up to the highest point, it comes back, and after 4 seconds it is back to its original position. Then it overshoots that position and it goes down. In other words, after 5 seconds, the position will be 25 meters below the throwing point. And hence, because displacement is a vector quantity, that indicates that the object has a negative displacement. And the negative displacement indicates that the object has overshot its original position. Now, if we are to draw the velocity time graph, for the velocity time graph, we will use the equation V is equal to, V final is equal to V initial plus A delta T. Now what we have, then we will be having time in seconds. And then we want to find the velocity in meters per second. So we still have 0, 1, 2, 3, 4, 5 as the question suggested. Now in this one, we'll still take up as positive. When our time is 0, what happens? This becomes 0, the acceleration will, this quantity multiplied by 0 becomes 0. So we have V final will be equal to V initial, which is 20 meters per second. So here we have 20. When V final, okay, when we use the same equation, V final is equal to Vi plus A delta T, but the time now is 1 second. What we get will be V initial is 20 meters plus A, which is our 10. Remember that our acceleration is acting downwards, and then the time will be 1 second. So this gives us 20 minus 10, which gives us 10 meters. We can continue with that. We will find that as we do that, when t is equal to 2, then this will be 20 minus 20, which gives us 0. When t is equal to 3, we are going to have 20 minus 30, which gives us minus 10. When t is equal to 4, then we have 20 minus 40, which gives us minus 20. And when t is equal to 5, that is 5 multiplied by that will be -50. So we have 20 minus 50, which will give us minus 30. Now when we plot these points on a velocity time graph, we will realize that at t is equal to 0, our initial velocity is equal to 20. When t is equal to 1, our velocity is equal to 10. When t is equal to 2, our velocity is equal to 0. So our graph, if we look at it, we will realize that at the time when we project this object, we project it with an initial velocity of 20 meters per second. That is at the point of throw. The velocity of this object, because the object is going up and at the same time is accelerating downwards, its velocity decreases, hence why our slope of this graph is negative, or it slopes to the left. What we also see as the relationship here is that at time 2 seconds, when the object is at its maximum height, the velocity at that maximum height, which is the final velocity, is equal to 0. The object goes up according to the position time graph, and then it comes back to the starting position after 4 seconds. So after 4 seconds, it is back to the starting point. But what is the velocity of that object? The velocity of that object, if we look at this, we find that it is -20 meters per second. And what does this tell us? It is -20 meters per second. In other words, it is the same velocity that it started with. Notice it is at the same point. So this gives us a straight line, which is having a negative gradient. Key points to note here. The initial velocity with which we project the object is the same as the final velocity at which the object comes back to the position of throw. At the highest point, the velocity is actually 0. And when we get to the acceleration time graph, for the acceleration time graph, what we do would be to take the acceleration is equal to the change in velocity over change in time. And here, if we take for the first second, we will notice that the change in velocity will be 10 minus 20. Divide that by 1 minus 0, and that gives us -10 meters per second squared. We can do this for the second. This will be 0 minus 10 divided by 2 minus 1, which is going to give us minus 10 meters per second squared. Now what this tells us is that if we were to plot these points, we will realize that the acceleration at time 1 second, the acceleration is minus 10 meters per second. At time is 2 seconds, the acceleration is still minus 10 meters per second. At time 3 seconds, the acceleration is still minus 10 meters per second. This tells us, therefore, that the acceleration remains constant and it is always negative in this particular respect because the gravity is acting downwards and we chose our direction upwards as positive. These three graphs are the graphs that we actually come across when we deal with a vertical projectile. So if we know this relationship, then we can always be able to deal with questions. Now, a question here comes from you learners, that why am I making acceleration of gravity 10 instead of 9.8? The reason is that I am trying just to make these calculations for us as simple so that we can see the shape of the graphs, not necessarily the values as they are. If we were to use 9.8, then we would not have whole numbers, simple whole numbers that can fit into the graphs. So this is just an example so that we can look at the pattern, the nature of the graph of the position time graph, the velocity time graph, and the acceleration time graph. At this point, then, I will pause to say, so when we substitute the acceleration due to gravity in our questions, we will always use a 9.8 depending, not necessarily depending. We'll use 9.8 because that is the acceleration due to gravity of an object. I think now it will be time. Let's put in mind these three graphs as we try to look at a few exemplar questions. I will be looking at multiple choice questions on vertical projectile motion, and these are the questions that you have actually got from the past examination question papers. They are compiled so that you can be able to use them for your revision. Learners, as you can see here, I have tried to highlight some important aspects, some important terms. When you read the questions, remember to highlight important statements so that you can be able to be guided by them as you answer the questions. Secondly, it is important also when you do your calculations to look at to determine the direction. Choose your own direction. If you choose up as positive, then you can be able to work with that. Alternatively, if you choose your direction as negative, you can also be able to work with that, but you will eventually come up with the same answer. Now let's look at this question. Question 1 on the multiple choice. It says, a stone is thrown vertically upwards and then it returns to the thrower's hand after a while. It returns to the thrower's hand after a while. Which one of the following position time graphs best represents the motion of the stone? Now if I can go back to the graph that we drew, our position time graph says we start at that position, the object is projected upwards, it reaches a maximum height there, and then it goes back to its original position. I think from this already we see that this object comes back to the original position, where the position initially is the same as the position after. It goes up and then it comes down. And I think that graph answers that. This graph shows the position of the object. When it is thrown up, it goes up to the highest point and it comes back to the original height. Now if we look at the first one, the object started at this position, then it goes up, and when it comes back to the point of throw. It is indicated here, but it still shoots down past the position of throw, which would be representative of this graph, the whole of this graph. So what we are interested in here is just a part of this graph which shows that the object goes up and then it comes back to its original position of throw. So this equation will be this graph will be the one that most correctly represents our situation. We will not talk about this because it represents straight lines. Now if you look at the motion, the position of an object, it is not actually a straight line because the object is accelerating. It's decelerating, its speed is reduced, so the graph cannot be a straight line but rather a curve. So these two graphs will not be applicable. So that leaves us with graph C for that. Question 2. It says a stone is thrown vertically upwards and it returns to the thrower's hand after a while. It's thrown upwards and it comes back to the thrower's hand. Now they say which one of the following, we are looking at velocity time graph. Now the velocity time graph, as we indicated earlier, is a straight line graph. And in this case, we are saying a stone is vertically thrown upwards and then it returns to the thrower's hand. This represents the situation similar to the one that we have here. This object was thrown up with an initial velocity. It goes to the highest point, so its velocity is 0 after 2 seconds. The velocity, it changes direction and the velocity increases in the opposite direction to that. So you notice that based on the graph of position versus time, when the object starts there and it goes back to its original position of throw, the initial velocity with which it was projected upwards will be equal to the final velocity, but they will be in opposite directions. Let's look at that. Which of these graphs do you think would represent the situation? The initial velocity is high. That's where it started. The velocity decreases as it goes up. It reaches a maximum point at that where the velocity is equal to 0. Then it comes back to its original position. This graph will be more similar to what we had here. and that will indicate the correct graph. This, if we look at C, for example, C will just indicate that this velocity is the velocity at which the object is thrown upward or projected, but the velocity decreases to 0, so this will be the velocity when it gets to the maximum height. So this would not be correct because it doesn't go back, it doesn't represent the velocity when it goes back. This graph would be a speed time graph where the direction is always positive. Or yes, the direction is always positive. So it shows that the speed decreases up until it goes, but when the object comes back, the speed increases. It is not negative because speed is a scalar quantity, whereas velocity is a vector quantity. So this side, the velocity is negative. So the correct answer there will be B. Perhaps now the idea of this activity comes into play when we deal with these questions. Now we realize how important maybe our understanding of the position time graph and the velocity time graph, the relationship thereof assists us in trying to work out questions. Now let us look at number 3 here. It says an object is projected vertically upwards. An object projected vertically upwards reaches its maximum height and returns to its original point of projection. This is the same. In fact, the 3 questions are more or less the same. Now they say we should ignore the effects of friction. The direction of the acceleration of the object during its motion is... Now we are talking about the direction of the acceleration of the object during its motion. Now we can best understand that if we look at the velocity time graph, the object is projected vertically upwards. The velocity of the object is decreasing up to a maximum, and the object then changes direction and the velocity is increasing in the opposite direction. Because our graph slopes to the left, this shows that the slope, the gradient of the graph is negative, and therefore the acceleration is negative. We also note here that this is a straight line graph. Being a straight line graph, the slope of a straight line graph is a constant. That tells us that our acceleration is negative, and if the acceleration is negative, the acceleration is also constant. So we will say that the direction of the acceleration of the object is directed vertically downwards because the object's acceleration is towards the center of the earth. So in this case, if you project the object upwards, it will go down. It will accelerate downwards. So its velocity as it moves up decreases. So according to this, the acceleration will be downwards. This one says it will first vertically be upwards and then it will be downwards. Acceleration, as we see from the graph here is constant and is negative. We can also see here the acceleration for an object that is thrown upwards is negative, and it is because it's negative, it is below the x-axis, below 0, and it is constant. So we cannot say that the acceleration changes. It becomes, it points downwards in one situation and then it points upwards in another situation. It is always constant because it is the slope of a straight line. D says always vertically upwards. This cannot be true because we know that objects tend to fall towards the earth as a result of the gravity or the acceleration due to gravity. Question 4 says a ball is released from rest from a certain height above the floor and bounces off the floor a number of times. Here the object bounces. Then we are given the position time graph, which represents the motion of the bouncing ball from the instant it is released from rest. Now, what are we going to check here? They say this is a position time graph. Now, it represents the motion of the bouncing ball from the instant it is released from rest. Now, they say neglecting a resistance, which point A, B, C, or D on the graph represents the position time coordinates of the maximum height reached by the ball after the second bounce. We are looking at the second bounce here. We are looking at the position coordinates. Let's try to understand what is happening here. This object, because we are talking about the position, is thrown from a certain point. It goes down. Now, as it goes down, it is actually accelerating because the curve is not a straight line. It is accelerating. But we must understand that we are taking down as positive. So as this object is accelerating, its velocity increases, or as it's dropped, its velocity increases. Therefore, its acceleration is positive, hence why you see that. When it hits the bottom, it changes direction and it starts to move towards the point of throw. And as it moves towards the point of throw, it decreases its speed, so it is moving towards the point of throw. But of course, because it has bounced, it doesn't reach the maximum point of throw. Then it comes back, it accelerates. So you look at this part, it's the same as that part. It accelerates and then it hits the ground again. It goes back to the original position. So this B will be the first bounce, D will be the second bounce, where it tries to approach the highest point, but because it has lost due to contact with the ground, it has lost some energy. It doesn't actually come back to the original point of throw. So that will give us a D as the answer to that. Let's look at the next question. A ball is released from rest from a certain height above the floor and bounces off the floor a number of times. So it bounces off the floor. This is similar to that one. It's a bouncing ball. They say ignore the effects of air resistance. Then they say which one of the following velocity time graph best represent the motion of the ball. Now we are looking at the velocity time graph. This is interesting because I will keep on referring back to this graph, because in a way it tells us this object is released from rest. So it's similar to the first one where the object is released from rest. But now we are concentrating, or we are concerned with the velocity time graph. For an object that is accelerating, the velocity time graph becomes a straight line. So since it is a straight line, we can very quickly look at the fact that these two equations graphs do not give us straight lines. So we can immediately eliminate this. We have these two graphs, C and D, where this one gives us a straight line but with broken lines. We would probably associate this with the acceleration of an object because it remains constant at that interval. But the graph which illustrates the velocity here, if we relate it to that, to the first question, we will notice that when this object is released from rest, its initial velocity is 0. Because it is moving, let's say it's dropped and it's moving downwards, its initial velocity is 0, so the velocity increases up until it hits the ground. When it hits the ground, then it changes direction. And you notice that the velocity is a straight line and the acceleration is constant. So the correct answer for that will be C. We can easily eliminate these two because they are, and this one says the quantity, the velocity here is constant, but it is not constant because for any object that is released from rest, if it experiences gravity, it is going to accelerate. Therefore, its velocity is going to increase. So that leaves us with C as the correct answer. To round off, the last question that we'll look at is the velocity time graph below, which is question number 6. The velocity time graph below represents the motion of an object. Which one of the following graphs graphs represent the corresponding acceleration time graph for the motion of the object? The object, or the graph, is a velocity time graph, so it is a straight line, represents the motion of an object. Now, can we try to understand what is happening here? The object starts with a certain velocity. The velocity in this case increases. If we look at the positive, the slope of the graph is positive. That means the acceleration is positive. So the velocity increases from a negative value to 0. Then it increases there again. So we realize that if this is a velocity time graph, the slope of the graph is positive. And if we were to compare our originals, we will see that for this graph, the slope was negative. It is also a velocity time graph of an object which is projected upwards. The slope is negative. But if the slope is negative, that corresponding acceleration time graph is negative, and because of the slope which is negative, and this is constant. For this graph, the slope is positive, the acceleration is constant, and it is positive because the slope of a straight line is positive. Therefore, we look at the possible answers as this one, this 2. D has a negative slope, which means that the graph would have to be sloping to the left, and therefore the only one that has a constant positive slope is C. This 2, because the acceleration according to this graph's change, then this does not represent constant acceleration, and A and B cannot be the answers. We will take a break, after which then we will go on with the calculations on longer questions that require us to do some calculations.